Hello, and thank you for the opportunity to present my work on a protoplanetary disk observed by ALMA. This work was recently accepted for publication in APJ Letters. This is the archive number. And these are the collaborators involved in this investigation. I'm going to talk about star and planet formation, and because of this, I want to give a brief some thoughts on accretion processes. As we know that accretion is very prominent in the earliest phases of star formation, where the cloud is collapsing into dense cores and disks. This process can be very energetic and, for instance, drag magnetic field lines or bend magnetic field lines, which are otherwise agents of resistance against the gravitational pull. Accretion is also a self-similar process, as it can be observed over a variety of spatial scales, from, for instance, 10 to 10,000 AU, as was recently reported, this accretion filament from a cloud into core, bringing fresh material, fresh chemistry from the cloud into these cores, but also at smaller scales, where we see the core envelope accreting into young circumstellar disks and observed like 1,000 and hundreds of AU through these patchy filaments surrounding the disks. So, but when this core is fully accreted into the disk or dissipated because of outflows, the material in the disk is reprocessed and delivered to the protostar or to planets in the disk structure. Exoplanets, we know it's the increasing number of exoplanets due to the variety of methods to observing them covers a large parameter space of white orbits and masses, for instance. These planets are formed in protoplanetary disks. And as we see here in this D-sharp, in the D-sharp survey, these protoplanetary disks, the signature of planet formation are these rings and gaps observed in this kind of objects. So Barnard 59 is a dense core hosting a protocluster with YSOs, young cell objects at distinct ages, as we can see for the distinct shapes of the SED, near infrared and mid infrared SED. We recently published a paper on the youngest member of this cluster, showing a flattened dust envelope accreting into a disk, which turned out to be a circumbinary disk, which was in turn accreting into these tiny circumstellar disks. The accretion takes place along these spiral filaments, which is again another case of accretion going on in that previous scale that I showed, but going down to very small spatial scales. But now I'm interested in another member of this cluster, which is called BHB2007-1. Is this object here in the Herschel image? It's a bit isolated from the rest of the cluster. These are the properties reported by previous works. And about this object, it's a bit more evolved young stellar object as a class 1, 2. And this is how we see it with ALMA. This is a dust continuum image, this is the CO emission, and these are the intensity profiles from a cut along the major axis of this object. So in dust, we do see a clear gap to dust minima surrounded by the inner disk and by the outer disk, and a smooth CO distribution that decreases with radii. So the gap is about 70 AU, and what we are seeing here is actually an edge-on protoplanetary disk. So this is an inclination we found 75 degrees. These are other parameters like the radii and the position angle of the disk in the sky. The CO emission shows this the clear velocity gradient showing the rotation direction. So the rotation axis will be in this direction, and this X shape, which is consistent with a flared disk. When we inspect the CO emission channel by channel, we see that the channels where emissions are coming from the cavity has a very intriguing aspect, as the blue shifted emission from the southern side of the cavity is much brighter than the red shifted emission from the northern side. So this big asymmetry is interesting, implies that in the southern side of the cavity, we have a very hot gas, it's about 100 K, hot and compact, because when we see it in velocity, it's also very compact. In the position velocity diagram taken along this, from the CO emission along the major axis, we do see that this blob, so that in the third dimension velocity space is also very compact. So it's in the 3 dimensions, it's a very compact object. And more interestingly is that coinciding with this position, we also detect radio emission. We use the very large array to observe this object in 22 gigahertz. We found 2 spots. So the primary one is we call VLAE1. It's a radio jet centered in the protostar in a disk. But we also detect the secondary component, which is very faint but significant and coincides in position with the zone of hot molecular gas. These are the properties of these VLA VLA spots. They're both consistent with free emission produced by ionized gas. The secondary spot is interesting because since there is no counterpart in dust, this reinforces that it's a fairly flat spectral index that is consistent with this kind of emission. So the radio emission plus the hot molecular gas implies that we are seeing a substellar object being formed in the cavity. This could be a giant planet or a young brown dwarf. Giant planet, we know this due to their accretion luminosity, they can warm up the gas around the molecular gas around it. But it could be also ionized winds and jets from a accreting brown dwarf or emission from the magnetosphere of a fast rotating brown dwarf. This is consistent with this correlation that exists between bolometric luminosity and symmetric emission from young stellar objects, where the relation prevails down, exists down to brown dwarfs and very low luminosity objects. So we could be seeing this kind of object. We model the disk using a prescription of Leidenbell and Pringle of a viscously evolving disk. We have parameterized the disk using the specific values of surface density for the gas, also radius where this surface density changes the regime from power law to exponential. Also dust MRN distribution using 2 populations of dust size. So you can find more details of the models in the paper. We ran the torus radiative transfer code, and among the grid models that we used, the best model is one with the inner disk with outer edge of 20 AU plus cavity in dust, completely empty in dust, of 70 to 75 AU in width. This is the model, and the white contours is the data. So we can see that they're very consistent. We also tried to model the CO emission, but use a line. But we know CO is optically thick, so we could not see any gap in gas until the depletion factor in gas was higher than 100. Otherwise, the gap was hidden by the high optical depth of the CO. But thus, we do believe that there is some gas in the gap. We use these values to constrain the companion mass using a similar approach than D-sharp, the D-sharp team that uses the width of the gap with respect to the disk radii, and all the parameters like the dust distribution also with the 2 population size and disk viscosities. And we found that this gap has to be produced by a substellar companion with a mass range between 4 and 70 Jupiter masses, which is actually consistent with the radio emission, as this is the mass required to launch ionized winds and jets with this value of free radio emission. A second interesting aspect of this source is that the disk is surrounded by very large filaments of gas. What you see here is CO data, CO emission. These structures are more or less 2000 AU in extent. They are aligned with the disk major axis, so perpendicular to the rotation axis, and they are very narrow in velocity. This is about 1 kilometer per second each lobe in width, and you almost see no velocity gradient along this structure. These, and besides, the velocity of these components are only 2 to 3 kilometers per second with respect to the systemic velocity. All of this imply that what we are seeing is accretion into the disk, is low accretion into the disk, and that this accretion happens mostly along the plane of sky. If we do a simple model of the line of sight velocity, we do see that it goes to 0 because of the projection of the direction of these motions along the plane of sky. And we even see the Keplerian component here prominent when we approach the disk. So this is the CO, the distribution of CO over distance. This is consistent with the large picture, as we do see patches of dust patches connecting the bulk of gas in B59 into our object. This is our object, and we do see these patches here, not only in dust, but also in molecular gas. You see 13CO and C18O, which means that we are seeing a protoplanetary disk, which is actually still accreting, and this accretion can still affect the planetary system that will be born in there. So this is not an isolated disk. We do see accretion, as I said, and this accretion can be affected not only dynamically, but also chemically, if depending on the chemical content of the material that is going to come into the disk, and it will affect the chemistry of these future planets that will be formed in there. So summary and takeaway message: accretion is a self-similar process from clouds to star. And we reported ALMA observations of a protoplanetary disk, which is already forming planets, but keeps accreting material from the parental cloud. This accretion, the accretion filaments are huge, 4,000 AU. And in this, the planet or brown dwarf formation is derived by other methods like the radio observation and molecular line observations, with asymmetric, very bright lines in one side and not the other. And this accretion can affect the chemical composition and the future planetary system that will be formed in this disk. This also puts new time constraints on the planet formation and disk evolution. So I wanted to thank you very much for your attention, and I will be happy to answer any question or discuss anything you want. So thank you very much.